There's a class of engineering problem where the hard part is not the machine. It's the fact that the machine has to hold still while the thing it is pushing tries to boil it. Moving a house is a solved problem. You jack it off the foundation, you put it on a truck, you drive slowly. Moving a city block is harder, but not different in kind. Moving a mountain has been done, badly, with explosives. Every one of these is the same problem scaled up, and scaling up is something engineers know how to do. Now take the sun. Not a metaphor for the sun, the actual object. A ball of plasma, 865,000 miles across, weighing 2,000 trillion tons, burning 4 million tons of itself into light every second. There's nothing to grab. There is no surface to push against. Anything you build near it evaporates, and yet the physics of moving it is not in dispute. The equations were published, checked, corrected by a second paper, and published again. We now know how to move the sun. We just can't build the thing that does it. Not because the idea is wrong, but because we don't have the material. The blueprint exists, and the bricks don't. And that gap between the two is one of the strangest positions science has ever been in. A design that is finished, correct, and physically impossible to construct with any substance that currently exists on this planet. This is the dilemma, and working out exactly where it breaks tells you more about the limits of matter than any amount of speculation about alien civilizations ever could. Most people have met the Dyson sphere, a shell, or more realistically, a swarm, built around a star to capture its output. It shows up in science fiction constantly, and it has become shorthand for an advanced civilization. But a Dyson sphere only answers one question: where does the power come from? It's a battery, an extremely good battery wrapped around the largest power source in the solar system. But a battery all the same. It sits still, it collects, it doesn't go anywhere. The star engine is the other half of that sentence. If the sphere is the battery, the engine is what you plug into it. And the reason you would want one has nothing to do with curiosity and everything to do with the neighborhood. The galaxy is not a museum. Stars drift. Every few 100,000 years, another star passes close enough to disturb the outer solar system, and the gravitational nudge sends comets inward on new orbits. Molecular clouds, cold and dense at hundreds of light years across, drift across the plane of the galaxy, and passing through one would strip the heliosphere and change the climate of every planet inside it. And somewhere in the next few million years, a star massive enough to go supernova will end up close enough to matter. Not close enough to sterilize the Earth, probably. Close enough to strip the ozone layer is a much lower bar, and it gets cleared more often. A civilization that plans on lasting has to eventually notice that it lives on a moving target inside a shooting gallery. And once it notices, the question stops being philosophical. It becomes logistics. How do you move a star out of the way, and how much lead time do you need? The answer to the second half turns out to be the hard part, and it is where the whole idea starts to feel like engineering and more like a religion with a very long calendar. One quick thing before we get into the machines. If you want more of this kind of thing, the version where we actually check the numbers, subscribe and turn on the bell so the next one finds you. The first design is also the simplest, and it was published in 1987 by the Russian physicist Leonid Shkadov. It has no moving parts. It burns no fuel. It is, in essence, a mirror. Put an enormous curved mirror on one side of the sun, not orbiting in the ordinary sense, held in place by a balance between two forces, the sun pulling it inward with gravity and the sun's own light pushing it outward. Get the mass per unit area right and those two cancel exactly, and the mirror simply hangs there. Shkadov's version is roughly 93 million miles across, which is about the distance from here to the sun. Here's what it does. Sunlight leaving in that direction gets reflected back. Light carries momentum, so the reflected light pushes the mirror one way and, by reaction, pushes the sun the other. The sun becomes its own engine, firing continuously with the mirror acting as the nozzle. It's a solar sail with the roles reversed. On a normal solar sail, the light pushes the sail and the ship moves. Here, the sail refuses to move and the star does instead. So, how fast does it go? This is where the fantasy meets the arithmetic. The acceleration works out to about a trillionth of a meter per second squared. A snail moving across the table accelerates roughly 100 billion times harder. You would not detect this with any instrument on Earth. You would not detect it with any instrument we know how to build. But acceleration is patient. Run it long enough and the numbers stop being ridiculous and start being merely absurd. Caplan's analysis puts the deflection at roughly 100 light-years over one full orbit of the galaxy, which takes about 230 million years. Under generous assumptions, the figure could reach 1,000. Sit with that for a moment. 230 million years ago, the first dinosaurs had not appeared. The continents were one mass. If a civilization had switched on a Shkadov Thruster and then walked away, the payoff would be arriving right about now. No institution humans have ever built has lasted 10,000 years. The oldest continuously operating one is a religion, and it's not close. A Shkadov Thruster does not require better technology than we have. It requires a civilization capable of caring about an outcome 20,000 times further away than any of our institutions have managed to persist. That's not an engineering constraint. It is something much harder to solve. In 2019, the physicist Matthew Caplan published an alternative, and it is a genuinely different animal. Where Shkadov reflects, Caplan consumes. The design is a fusion engine parked near the sun, powered by a Dyson swarm that does something no rocket has ever done. It takes a propellant from the object it is pushing. Electromagnetic collectors scoop hydrogen and helium out of the solar wind and off the surface itself. The hydrogen goes into a fusion reactor. The helium is fired out as a jet. Then comes the part that makes it work. The engine fires two streams. One jet of helium is aimed away from the sun, providing thrust in the ordinary way. A second stream, hydrogen, is aimed back into the sun, and its job is to hold the engine in place against the recoil that would otherwise push it away. It's a tugboat that feeds on the ship it's towing, and it stays attached by continuously pushing back on it. The exhaust velocity runs up to about 62,000 miles per second, which is a third of the speed of light. The performance difference is not incremental. Caplan's engine accelerates the sun about 1,000 times harder than Shkadov's mirror. In the language of the papers, passive designs produce large deflections on billion-year timescales, while the thermonuclear ramjet produces them on million-year timescales. A 1,000-fold improvement moves the project from geological time to something a very determined civilization could plausibly plan around. The cost is the appetite. Feeding the engine means consuming millions of tons of solar material every second, and sustaining that for 1,000,000 years means eating a serious fraction of the star. Caplan's own figures assume roughly a quarter of the sun ends up as propellant. There is an odd consolation in that. A lighter star burns cooler and lives longer, so a civilization that spends a quarter of its sun on moving house also buys itself billions of extra years of daylight. The engine is destructive and life-extending at the same time, which is not a trade-off that shows up anywhere in ordinary engineering. And still, none of this is the reason we cannot build it. Fusion is a problem we are actively working on, and a civilization with a Dyson swarm has clearly solved it. The scoops, the magnetic confinement, the jet geometry, all of it is hard, and all of it is the kind of hard that gets easier. The wall is somewhere else, and it is the one place engineers cannot argue with. Every design above assumes a structure that can sit close to a star and not die. That assumption is doing an enormous amount of work, and it is the assumption that fails. Start with heat. The surface of the sun runs at about 10,000 degrees Fahrenheit. The corona above it, counterintuitively, is far hotter still, over 1,000,000 degrees Fahrenheit, and often much more. Now compare that to the best material we have. Tungsten melts at 6,192 degrees Fahrenheit, the highest melting point of any material on the periodic table. It's not close. It's not within a factor of 2. Put the best refractory metal humanity has ever produced where these machines need to sit, and it does not warp or soften. It leaves as a vapor. There are ways to cheat, and they are worth naming because they are the reason the designs are not dismissed outright. You can put the structure further out where the flux is lower. You can make it reflective enough that most of the energy never gets absorbed. You can make it thin enough that it radiates heat away as fast as it takes it in. Every real proposal does all three, but each of those fixes trades away thrust, and past a certain point, you have built a machine that survives beautifully and does nothing. And then there is the second problem, and it's worse because it can't be traded away. The structure has to be enormous, and it has to be almost weightless. Enormous because catching a meaningful fraction of a star's output means spanning a distance comparable to a planetary orbit. Almost weightless because the whole scheme depends on the balance between gravity and light pressure, and light pressure is feeble. Get the mass per unit area wrong and the mirror either falls into the star or gets blown away. So how strong would it have to be? Structural steel fails at somewhere around 80,000 psi. Graphene, the strongest material ever measured, reaches roughly 19 million psi in a single perfect sheet. That's more than 200 times better, and it sounds like the answer. It's not, and the reason is the phrase single perfect sheet. Graphene achieves that number in flakes measured in fractions of a millimeter with no defects. Strength in real materials is not set by the average bond, it's set by the worst flaw. One misplaced atom becomes a crack initiation site, and the crack does the rest. We can grow graphene by the square meter now, and the moment we do, the measured strength collapses towards something ordinary. Scaling a perfect crystal to the width of a planetary orbit is not an incremental manufacturing challenge. Nobody has produced a flawless crystal a single meter across of any material ever. Carbon nanotubes have the same story and the same ending. The space elevator has been waiting on exactly this problem since the 1960s, and a space elevator needs a ribbon a few tens of thousands of miles long. A star engine needs a structure millions of times larger, sitting in a furnace. This is the real answer to the question in the title. Not energy, which a Dyson swarm supplies. Not physics, which is settled and published. Not even fusion, which is a matter of time. We can't build a star engine because we cannot make a perfect thing that is also a big thing. And every year of materials science has made that limit look more fundamental rather than less. There is an obvious worry here, and it deserves a straight answer because the obvious version is wrong. The worry goes like this. If you accelerate the sun, the planet gets left behind. The sun pulls away, the Earth does not keep up, and we are abandoned in the dark. It is an intuitive picture. It's also backwards, and the arithmetic is not close. The sun's gravity holds the Earth in orbit with an acceleration of about 0.02 feet per square foot. The best star engine on the table produces roughly a billionth of a meter per second squared. The gravitational grip is millions of times stronger than the tug of the engine. The solar system comes along intact without noticing. You could not shake the planets loose with these designs if you tried. But there is a real orbital problem, and it is more interesting than the fake one. The Shkadov mirror works by intercepting sunlight. Sunlight that hits the mirror does not reach whatever is behind it. Point the thing carelessly and you have built the largest sunshade in history directly over the ecliptic, and you have solved the problem of a nearby supernova by freezing every planet you were trying to save. The fix is geometry, and it constrains the mission. You put the mirror over a pole where the planets never go, but a mirror at the pole can only push along the polar axis, so a civilization cannot simply choose a destination. It gets one direction perpendicular to the plane its planets orbit in, and it has to make do. Steering in the ordinary sense is not available. Later designs try to solve exactly this, and they add complexity fast. There is a subtler version too. The engine sits at a fixed point relative to the sun and pushes while the sun pulls it back. Every design in the literature spends real effort on station keeping, because a structure that drifts is a structure that eventually falls into a star or leaves the system. The Caplan Thruster second jet exists purely for this. It's not a detail, it is a substantial fraction of the machine. So the honest picture is not that the planets get flung away, it is that a star engine changes the sky permanently, restricts where you can go, and demands active control forever. You do not just switch it on and coast. Somebody has to be minding it continuously for longer than complex life has existed on Earth. Put the pieces together and the shape of the problem is clear, and it is not the shape most people expect. We are not blocked by physics. The equations were written, published, corrected by a second team, and they hold. We're not blocked by energy because the same civilization that builds the engine has already wrapped its star in collectors. We're not really blocked by fusion either, which is difficult but not mysterious. We are blocked by the fact that atoms will not hold still in large numbers. Every material we know fails when you make it big enough because bigness means flaws, and flaws mean failure. That is the wall, and it is the least glamorous obstacle imaginable. No paradox, no exotic physics, no missing theory, just the stubborn refusal of matter to be perfect at scale. And then the second wall, which is not made of matter at all. Even the fast design needs 1,000,000 years of continuous operation. The slow one needs 230. We have no institution, no language, no religion, no country that is held together for even 1% of the shorter number. The machine is a materials problem. Keeping anyone interested in the machine is a problem we have never come close to solving. There is a version of this that reads as defeat, and it is the wrong reading. Every ship that has ever crossed an ocean was drawn in sand or scratched on bark by someone who could not build it. The drawing came first, sometimes by a very long way. What Shkadov and Caplan did was not fantasy. It was the drawing. Someone worked out precisely and checkably what a machine that moves a star would have to be, and now that specification exists, and it will still exist when the materials catch up or when it becomes clear that they never will. That is a real result either way. Knowing exactly why you cannot do something is not the same as not knowing how. So here is the question worth arguing about in the comments, and it is not whether we will build one. If you had the engine and you had the 1,000 years of patience, where would you steer the solar system? Toward the nearest star in a system we can actually reach? Out of the galactic plane, away from the traffic into empty space where nothing passes close ever again? Or would you leave it exactly where it is, on the grounds that a species that cannot manage a century of planning has no business steering a star? Tell me below. And that mirror has to sit over a pole because the space directly above and below the sun is nothing like the space around it. That is a stranger place than most people realize. Watch what's directly above and below the sun. It's on screen right now.